that you can repeat it if needed. Okay, please remember correlation. So we have chapter 15 was correlation, 16 regression, 17 chi-squared. So correlation and regression really deals with the use case of two continuous variables that you have, dependent continuous and independent continuous, as opposed to continuous dependent and categorically independent as we had for the hypothesis testing before, particularly with t-test and ANOVA. So we are trying to establish here associations and the strengths of associations, including the directions with the computation of a correlation coefficient that essentially is calculated with the formula stated on this slide. Did I find it? And this correlation coefficient essentially incorporates a standardization step. So we have the sum of the product of all individual deviations, not squared. So that's important because that's how it preserves the sign and the direction of the association. And these deviations basically are then being divided by the square root of the product of the sum of squares of the dependent and the independent variables product. So that basically incorporates in itself as a metric, a standardization step. So this standardization is consistent with the standardization with standardization of individual scores in chapter 6. We have a deviation, we have a marker of the deviation of the means, here the product of both means divided by a marker, the product of that marker of individual variability of the dependent and the independent variables. So this standardization step is basically that step that is then useful when it comes to regression, where we essentially looking at the standardization of an individual X score of interest, 0 and 1, most namely in this case, because that standardization can then be used with this standardization marker that is characteristic for this association between those two variables to predict a standardized predicted Y. And this standardized predicted Y can then be utilized utilizing the standard deviation of the dependent variable to calculate back to a predicted actual Y value. And if you have the actual predicted Y value for an X equals 0, you know you have the actual intercept. And if you calculate the difference between an X equals 1 and X equals 0, you get the slope, which by definition is the increase or decrease, so the change in the dependent variable is an increment of 1 in the x-axis, a magnitude of 1. So we have discussed for regression, we discussed the example of the back depression score as a function of stressful life events, where basically we had 9.5 predicted intercept and an increase of 3.241 with each stressful life event experienced. So looking at this now in our correlation example, which was the example we did in module 21. It was earlier, it was module 19. So we have absences and exam grades. So basically, exam grades have a change as a function of absences. So if we were to calculate this as a correlation coefficient, we came to the determination by going through all the steps of computation of this correlation coefficient, that there's an inverse relationship. That means that there's a decrease in our exam grades with an increasing number of absences. So if this holds true, essentially this R square should be significant, as we've seen it is, because 0.72 is a particularly large R square. So basically we have an intercept of 94, this would be here, and we have an increment, basically a decrease with each increase of absence of minus 5.4. So this being said, the R squared, keep in mind what the R squared stands for. The R squared is basically the proportionate reduction of error. That essentially is, and I also only have the calculation here as we did it for the back depression score. So basically we have a total sum of squares for the dependent variable, which is the sum of squares as we have calculated it already as early as the standard deviation topic. So it's basically the square deviations of y minus my, and these sums gives us the sum of squares of the dependent variable, and that's the total variability of the dependent variable. That's all the variability. If we want to calculate then in the next step the R squared, we need first the residual error that is being created around the estimate of our regression function. So keep in mind, this is this graph, where we basically, if we are now coming from here, so that's our total error. That's the mean of y, that's the mean of our dependent variable, distance of each individual point. So that mean, this is our total error. If we're fitting now a regression function through that, we are basically using the least square approach to fit a regression function that will minimize these square deviations and minimizes the sum of squares. By doing so, we're basically decreasing now the sum of squares from 788 down to 526. So that's the leftover sum of squares. That's the leftover residual error. And the decrease of this residual error basically is that explained variability, that explained error. And this explained error is then calculated as a proportion of the total error. So this is that explained error divided by the total error gets us to the R squared. So that's here 33% was explained by our regression function. So now putting this into R. So we have now practice lab 5 is on your canvas. And we essentially have here on line 2, as usual, we're removing all the objects from the environment on line 2. We're then creating a new data frame on line 4 to 6. That data frame basically looks the same as the data frame we have in Excel. So it's basically 10 students, 10 absences, 10 grades. We can look at the characteristics of these variables. Well, there are various ways, right? One way would be to write summary. DFM22 gives you summary metrics for each of these variables. So it basically gives you here mean and the median of the absences, mean and median of the grade. So summary is quite a useful function. If we do LSDFM25 as stated on line 7, gives us absences, grade, and students. This is the name list of the variables contained in the data frame. We can now address each of these variables in our data frame individually. That's line 8, showing this essentially. So if you run just line 8, it basically gives you these individual entries for each student, just in terms of the absences. Just mapped out as a list. If you want to take this list of entries now and pack them into a separate object, so not a data frame anymore, but you grab them and you put them in a different object, and this object is then a list of data entries, a so-called vector. This can be done with line 9. So you're packing here DFM22 absences, this list of entries, into a vector, which then it looks a little different than the data frame there. So basically it's a numeric list of 10 numeric entries. Yes. Summary DFM22. So the same you can do with grades. So on line 10, you address DFM22 and you extract all the grades. Again, it's now a list of 10 numeric entries. These are all the grades that basically are contained in the variable. If you want to pack this and your line 11 looks to be a little bit different, so please change this. So there's absences twice, so line 9 and 11 are basically identical. Please change line 11 to grades, and after the $sign, this to grade, which is capital case G. So grade to basically do the same thing. So you address that variable and you pack the variable in a vector, a newly created vector. Line 12 is now basically using, just like we did in Excel, we used the choral function. We used the choral function. We use the choral function to basically do the same as we've done by hand by calculating the correlation coefficient. The choral function in Excel is choral and the two ranges of the two variables gets us the correlation coefficient. In R, that function looks a little different. It's core, C-O-R. It's basically core of an X and of a Y. So running this line, running line 12, is basically now calculating the correlation coefficient and packing it here. And this is the equal sign in R. We talked about this earlier. So smaller sign and hyphen indicates basically, so this is equal to this now. So basically assign this value to this object. So you're creating a new object, coef1, and you're assigning the result of this correlation to this object. So coef1 from now on basically is giving you just the number minus 0.85, which is from now on assigned to that object. If you want to go a step further, and we didn't do that yet in Excel, if you want to create now a regression model in R, you basically use the so-called LM function. And as you can see, that LM function is being in its totality assigned to fit1. So that becomes this model, contains all the components that this model calculates. So LM as a function basically stands for linear model. So you create a linear model of EFM22 grade as a function of EFM22 absences. That means your dependent variable is left of the tilde, and to the right of the tilde, you have all the independent variables. So now it created this linear model and packed it into fit1. If you want to see now what fit1 contains, you can address fit1 and show it in its entirety with line 14. So Control and Enter on line 14. First to run the actual line. So summary fit1 basically shows you now the entire model. And what the model contains is, it gives you a formula, which is LM following the formula of grade as function of absence. It shows you the residuals, gives you the residuals, distance of the individual observed data points to the predicted data point of the corresponding X. So basically, you get, for each data point, you get one residual. So now the distribution of this residual is meant for a regression, as we know, a normal distribution. So that should be normally distributed. In a perfect normal distribution, the mean and median should be identical. That means a point of interest is here basically the median, right? So we know that using a least square approach, the mean of these residuals needs to be 0 by definition. So because it's the distance of a least square approach, so you fitted it through minimizing the sum of squares. The sum of squares is calculated of the individual entry minus that actual observed entry. So the mean of the residuals of distribution of residuals is 0. The negative median, not corresponding with mean of 0, indicates that it's not perfectly distributed, not perfectly normally distributed, meaning that there's a skewness in one direction. And we can see that actually the max is positive. That kind of shifted the mean rather to the positive end. Thereby, the median is a little bit to the left of the mean. So there's a skewness, there's actually positive skewness due to outliers that are greater then the maxima, like the minima. So the maxima are greater than the minima, thereby towards the mean to the positive end. So we also have 25th and 75th percentile. So it is not a perfect normal distribution because of the outlier on the positive end. We also have the coefficients. So the coefficients are basically what we have looked at as intercept and slope. So the intercept here is 94.3, which we have also seen on the Excel spreadsheet. So we have on the Excel spreadsheet, we have 94.3 and we have a slope of minus 5.4. So this being said, around these slope estimates and the intercept estimates, we have a standard error. And the standard error is created by uncertainty around the predicted value. So this standard error here is 4.9 for the intercept and 1.12 or 1.2 for the slope. That results, as we know, with the standard error, it's easy to calculate the t. With a t, you can basically determine whether this is a significant coefficient or not. So whether the estimate is significant or not. And we can see here in the last column, we can see the actual p-value. Based on these standard errors, we can now, following the t distribution, we can determine with what probability that essentially is an accurate assessment. So we have here 0.002 for the slope, and we have here a very small number for our intercept. Those of you that are not, I hope all of you are comfortable with the scientific annotation. So basically you have 5.28 ln minus 0.8. That means that there are 8 decimals in between that 5.28 and the actual comma. So you have here then coding according to those asterisks. So R basically shows you the asterisks to the right. So 3 indicates it's at an alpha level, it's significant on alpha level of 0.001. Whereas 2 asterisk indicating 0.01 as the alpha level. Then you have a residual standard error, and this is the standard error of the actual predicted value, not just of the coefficient and the estimates. This is the actual full model. So you basically, so this is the sample population in its totality, creates a residual standard error of 8.8, which we could calculate essentially in Excel, on 8 degrees of freedom. Why 8 degrees of freedom? Because you have 2 coefficients, you have absences and the intercept. Both of those counts towards the degrees of freedom. Because both have here in the resulting prediction, they basically have both one redundant variable that can be dropped from the calculation of the sum of squares. Then we have an R squared is here 0.72. which is consistent with what we see here, and an adjusted R square of 0.69. Again, multiple R squared. The R squared is a proportional reduction of error, so that's basically the proportion of the total error that was explained by the regression function. If you include additional variables in your regression model, this R squared will by definition always go up, because you always will get better to explain something in your data. The problem is that comes at a price, because you may then introduce spurious associations in your regression model. Thereby, you need to some extent pay attention to which variables you include, how many variables you include, with which sample size. To adjust for the sample size and the number of variables, you use a new formula, which is the adjusted R square. I spare you this formula, but basically it's an adjustment for the number of variables and the number of and the sample size. So then you have an F statistic that basically is what quantifies the predictive accuracy of your model, basically taking the respective accuracy of each of these components into account. So this F statistic basically gives us an F of 21 on 1 degree of freedom. So this is intercept, and slope is 2 minus 1 for the sum of squares is 1 on 8 degrees of freedom on the vertically, which is the number of entries for each individual, resulting in a p-value of 0.002. So this is a significant model predicting the exam grades based on absences. So that's in a brief walkthrough what a model looks like, a regression model looks like. And now, any questions to that? Now we can briefly look into how to plot data. So plotting in R it's a little bit more involved at first. Once you know what is needed, it's simpler as an Excel, I find personally, because you just need to know the components that you pack into your code. So if you have plots, so the plot function basically plots, then you define an X, you define a Y, then you use XLab and YLab to basically label the axes. That's considerably simple. And if you change your data set and you add additional data point, you just need to rerun that line of code, and it basically will incorporate the new data points into your model as well, which can be super useful. So line 15 basically creates here your scatter plot. Line 16 basically utilizes the regression model from up here. You tell R, okay, so look, I have this regression model. I want to fit the lines through my scatter, and that line should follow that regression model. So basically, if you do fit 1, basically fits your lines through that corresponds with intercept and slope of intercept of 94, slope of 5.4, I believe. So that corresponds now with the regression function. And with text, you basically include the R squared, or now actually correlation coefficient, R, and that you query from line 12 from your coef1. That's your correlation coefficient. So basically you write text, you get with text, you give it a location on the plot where you want your text, and then you just paste coef for coefficient, and then you put the actual coef1 correlation coefficient in, and then the final product looks like this. So it's kind of useful, and it updates automatically. It comes with a lot of positive aspects. Or it can be automatically exported into PDF, and like you can do a million things. You can embed it in documents. You can, do wonderful things with that. Good. Okay, so this was our exam grade and absences example. So then we have DFM23, that's line 19. We press control and return there. It creates a new data frame. And that's now our back depression example. So we're creating now 4 different variables in our data frame, which is individual, so that's individual IDs. Then we have events, that's the stressful life events. And we have the back depression score, that's identical to what we have inside, and the sleep disturbance score, because we're going to build a multivariable regression. So if you click on DFM23, just go to the right in your environment. You have here on the right side, you have that spreadsheet-like symbol. That basically gives you the same spreadsheet as what you have in, where is it? Which you have here in your data. So this is here number of stressful life events, back depression score, sleep disturbance score. It's the same outline. You can, with summary DFM23, you can now look at the summary quickly, and these means will correspond with what we have calculated in Excel. So it's the same concept. So if you do now coef2, you're correlating now the back depression score with events. You get here a coefficient of 0.58, which is the correlation coefficient that we also got for our calculations here. So that's the same R. So we're doing now a linear model That's fit to A on line 24. That basically is built on line 24 and then queried on line 25. You get now the exact layout of that model. And again, you have the formula. Like the regression score is part of the sequence, median shift a little bit positive, again, max is larger than min, that means the shift is positive. Then the estimates, the standard error, the corresponding p-value, and the p-values, both, this one is like very close to 5%, so it is significant, but not too significant. This one is not even below 5%. Still indicated with a period by R, because sometimes these values, even though they are not significant, with a small sample size, they may still be biologically relevant or conceptually relevant for your research question. So that's why R is still marking them. So you have here the actual legend of which ones are basically considered at which level. Then you have a residual standard error of 8 and 8 degrees of freedom. Again, 10 individuals. 2 variables. Multiple R squared, you have 0.33. Adjusted R squared smaller than 0.25. F statistic and a p-value of 8%. So a non-significant model. So now that would prompt us to think whether we can do better than that. First, let's plot the data. Let's see what the variability is. 26 plots the data, 27 adds our slope, our fit line. 28 basically adds the correlation coefficient. So it's the same code as previously. But since we saw a non-significant model and we think we can do better, and we also have of our individuals the sleep disturbance score, and we know that poor sleep is resulting in an increased prevalence of depression. We're basically fitting now 29 and 30. And we're getting now our first multivariable. We know the coefficients already from the SPSS outputs. Yes.
For this summary before about the data frame 23, would it matter if it's like I submit it without, for some reason it's saying error? I don't think I wrote it. Like the data frame for 23.
That's fine. That was just extra curricular for my.
Thank you.
Okay, so we have a formula score as a function of events, and so you basically indicate additional variables with a plus sign. You basically get in addition the sleep disturbance score. You get again your residuals, because now you again residuals is predicted function. Whether this predicted function is consisting out of 2 variables, 3 variables, or 10 variables, doesn't make a difference to us. If you still get a prediction and you still get distance from an input data. So again, it's getting a little closer now to 0. The max and mins are a little bit smaller, but it is still not perfectly normal. So we have now estimates we have now estimates for all the included variables. So we have an estimate for the intercept. This is now negative. We have now an estimate for our event. So there's an increase of 1.2 for each additional stressful life event. And we have for each increase in this, and our sleep disturbance score, we have 2.1 increase in the back depression score. We have, and this is where it's getting interesting, and as you can see, the p-values here are different from the p-values we've seen in the initial model. And that's actually a powerful piece of information, because if that borderline significant variable loses significance in a model where you include a very powerful significant predictor, there's something going on. So in the selection of the variables you would include in a model, and this is far beyond the scope of this class, if you have a situation like that and you have an enormous information gain by including one variable, you only have a marginal small little information gain by including the initial variable, you may reconsider whether you actually need both. or maybe you're better off with actually one. So this information gain actually informs the selection of your variables. That they are quite sophisticated markers to actually quantify that information gain. So there's the so-called AIC and BIC, far beyond the scope of this class, but the AIC is the archaic information criterion, and BIC is the Bayesian information criterion. Basically gives you the level of accuracy and information gain of inclusion of additional parameters, and you have statistical methods to compare the models against each other. So, but that's how you would select those variables. And that becomes important because you have a multiple R squared and you have an adjusted R squared. And that already kind of also gives you an idea, because you have, with the inclusion of the additional variable, such an information gain that the adjustment actually only marginally decreases that R squared. So you have a substantially higher F statistic now because your accuracy got better and your overall model is now significant. Okay. So now when you have a model like that, there are a couple of assumptions regression models make that you need to pay attention to when you employ them. And these are mainly a linear relationship and homoscedasticity and a normal distribution. For this very topic and independent observations, obviously, but that's a given. Okay, so on line 33, you have, and this is where it's becoming a little tricky, you have so-called diagnostic plots. If you write plot and you're fit, you basically are being prompted here in the console, hit return to see next plot. If you hit return to see next plot, you see the first plot. And I just walk you through this, that you have seen it once. It's nothing you will need to know or explain for the files. I didn't make it appear. Oh, here we are. So what this basically is a diagnostic plot showing you fitted values and the residuals. So the dependent variable here is residuals, the independent variables are fitted values. So you have your actual estimates and you see whether with the magnitude of your predicted estimate, your residuals actually change. With the idea that you can see whether they are non-normally distributed or whether they are heteroscedastic, and they basically change in their variability over the range of your data. So these diagnostic plots are very powerful to essentially look at these things. You have here QQ plot where you basically see the same. You have standardized residuals as a function of theoretical quantiles. You have here scale again. This is standardized residuals as a function of the fitted values, and you have here standardized residuals as a function of the leverage that basically is an individual data point, and what the leverage of each individual data point is to actually skew your residual load. That basically gives you the weight of inaccuracy. But that's all. Just for the purpose of showing. What you please do now in your code, all of you, write a hashtag before the plot. Thereby you're hashtagging it out, and that makes it later for you, makes the practice lab access a bit easier. So hashtag in the beginning of line 33. So last but not least, any questions to regression? I think there are a lot of details, but it's like you don't need to know the details. But I think it's good that you've seen the capabilities that essentially exist with R and the sheer endless possibilities you have with this software. So if you go on line 36, you're creating now the table, and this is our coffee paper cup study. So if you run line 36, it basically creates a matrix utilizing on 3 rows. It basically adds exactly those values that we have used for our paper cup. Now, once we have this metric, and just to see the metrics at this point already, so we basically, this is just a skeleton of the metrics. We're going then on in line 37 and 38. We're giving it row names and call names. So column names and row names. And then the final product basically looks like what we have computed in Excel. So we have now our table, which is our paper example, our paper cup example. So this is the metrics. So now, if we want to run a chi-squared test now to basically compare expected versus observed, we can do this with line 41. So there's a function in R that basically runs a chi-squared test on our data. So the reason it needs to be organized in exactly that fashion that this chi-squared is actually running correctly. So if you run line 41 and then call x2, that's actually the result of the chi-squared test. So you have a query table, it calculates in chi-squared of 7.6, 2 degrees of freedom. Remember, it's the degrees of freedom row is 3 minus 1. Degrees of freedom column is 2 minus 1. 2 multiplied by 1 equals 2. And it gives you an exact p-value. The p-value that we have not computed, although we could have. So basically, it models out that entire chi-squared function and the entire distribution. The underlying function then is being used to calculate exactly with that chi-squared, how much more is area under the curve under that function beyond that calculated chi-squared. So now you can also on line 42, you can calculate your x2, or you can display your observed. So that is all contained in your chi-squared after you ran line 41. So if you click on LSX2, you see all information that can now be queried from that object x2. You basically can get all of this out, and it gives you all this information. So with x2 observed, you basically get exactly the input data. With x2 expected, you get the expected values. And remember the expected values. So we had in our Excel example, we had for recycling, we have 25 correct, so the incorrect for the unlabeled 25 and 30, so the if was 452. 52 divided by 3, so 2.3. Then we have for trash, we have 28 and 39. That's 68 and 98 and 107. 107 divided by 3 is 35.66 periodically. So you basically, you have here the expected just in the same way as we calculated it. And now, last but not least, and that's new from last time. I owed you that from last time, the calculation of the residuals. So the calculation of the residuals is now done in this fashion. So what you basically do is there are unstandardized and standardized and adjusted standardized residuals. If you standardize them, you basically calculate observed minus expected divided by the square root of expected. That gets you standardized residuals. And on your canvas, you have an Excel spreadsheet showing you exactly how to do that. So that's the example of observed recycled minus trash. So here's observed minus expected squared. This is observed minus expected squared divided by the expected. That allows you to calculate the chi-squared. So the standardized residuals are calculated as observed minus expected divided by square root of the expected. That gets you to the standardized residuals. If you go a step further and you calculate the adjusted residuals, you're literally going a step further because now you need to calculate, you need to, in the denominator, you need to take the expected for each individual row multiplied by 1 minus the row of the total proportion. So if it's if you have that count of 25, 25 divided by 52 would be that proportion of 1 minus 0.52 multiplied by 1. This is where the column comes in. So you basically have 25 divided by 53. That's the proportion here. So these are the adjusted residual, adjusted for the sample size in that cell in which you have interest. You basically calculate that for all your cells. And these residuals are then also to be computed in R. So here are the residuals. These are the standardized non-adjusted residuals. Yeah, and any questions to that? That was chi-squared in a nutshell. So that was basically the calculation in Excel, just quickly displayed in R. And I guess you can see the beauty of how quickly this can be done and how much information can be extracted within just essence 4 lines of code. Those 4 lines of code, you basically can do the same thing and more than we have done in half an Excel spreadsheet. So it's mastering this is certainly of value. Any questions on this? If not, then we can quickly do, well, we can complete practice lab 5. Make sure that you have hashtagged plot fit2b out in line 33. And just press Control and A. Run it with Control and Enter. Well, first Control and L. Clean the whole thing, Control and Enter. Select the entire computed console. Bring it in text edit file. And save it in your folder and submit it, please, as a TXT file via Canvas. So save. And please save it as STAT1021G, practice lab 5. Family name, and that's ready for submission. Yes.
Sorry, every time I always forget. How do you delete the bottom, the console again?
Control L.
Okay.
Or Command L. Oh, Control L. Sorry. Control L, Command A, and Control Enter or return. All right. Well, no question. Thanks so much. Have a nice evening. See you on Monday for